frequency of the sound, the wave, 8,000.
Is that big?
Small actually, low quality. With the computer, the higher the frequency of the microphone, the better quality the sound.
Or is it small?
8,000 is the smallest you can use.
Wow.
It's, you know,
Yeah, where do I for playing?
it's for playing games and for fun, you know, not for work. Not for work. Okay, interference. Does this word look familiar?
Yes.
Where have you seen this word before?
Wave. The interference
Wave.
of wave.
Maybe I gave you a little lecture last week about this? Yeah?
Maybe.
Interference?
Wave interference.
Yes.
I'll know the face.
Wave interference. Yes, that's right. Okay, continue. Quite a bit to do.
Wow.
So, what is interference?
Disturbance.
Come on, remember my lecture. What's interference?
Just like the threshold.
Like what?
Combine.
Thank you. Combining.
Oh, to create a new wave.
That's it. Interference is when two or more waves combine to form a new wave. This principle, yes, of superposition states that the net amplitude of the new wave at each point is the sum of the amplitudes of the individual waves. So I'll explain all of that in a moment. So when you did the lecture with me last week, you only had this much, right?
Yes.
That's because there were biology students there. I have to protect them. This is the full definition. I'll explain it once you write it down.
So that we're gonna learn about quantum physics.
What's that?
We're not gonna learn about quantum physics, right?
We'll touch on it briefly at the end. Very brief though. Not what we do.
Wave function.
No, not even that. Not even that.
My friend asked me what are you doing, and I said I'm doing something about quantum physics, and
Nice.
they said, wow.
Nice.
This is
Nice.
physics.
True, true. You can translate quantum physics into Chinese?
Yeah.
Oh, good.
I translate at the beginning. I know the topic.
Good. All right.
No.
No.
My friend asked me what I was doing for English, and it was easy, and I told him, oh, we are learning about quantum physics, and he said no more.
You handed in the assignment this morning, was it?
Yeah.
Too early.
Too early? Yeah. Okay, got this?
Send it, it's later than 8:30.
Then it said later than 8:30 or before 8:30?
From 8:30 to 8:35. That's when we can hand it in.
Wow. That's it?
A short window.
Very short.
Yeah, I saw Heron today morning jump into office.
Jump?
Yeah.
I was running. I was 2 minutes away from the deadline.
Very high.
But you made it. Okay.
Only 2 words.
Okay. You got this? Yeah.
Yes.
Okay, so let me explain this. So there's two words here which you know. The first one is interference, is when the two waves come together. But what we haven't said is when you have the two waves and they come together, so let's say, I don't know, like this, and you add these together, what do you get for the new wave? How do you add them? Well, the way it works, that's what the superposition part means. Superposition means the way you add them, and superposition means, you take the height here, you call that h1, and you take the height here, and you call that h2, and you add them together. So in this picture, maybe the height here is like 1 meter, and here is like -1 meter. So for that part, it will be 0. Here, you know, you have a small height, and here you have a small height. So maybe at the start, it's a big height. So I don't know. You'll get some graph But my point is, if we call this x and we call this h, and we call this x and we call this h, and this is h equals f of x, and this is h equals g of x, then the way you add them is very simple. You get f of x plus g of x. That's what I mean here when I say the net, the total amplitude at each point is the sum of the amplitudes of each wave. So I'll show you with my program here. So here's one wave. And then let's add in another wave. Oh no, that won't do. Right, so you can see the red wave and the black wave. So if I add these together, what I think will happen is, at the beginning they're both 0, and they both increase together, but then here the black one starts to decrease. So when I add the black one to the red one, its height should go down. So I'm picturing some wave that looks like this. It goes up and down, and up and down. Let me show you. So if I add them together, 1 plus 2, and draw, you can see it in green. Shaky, yeah. So this idea is called superposition, the way you add. So basically heights of waves add or subtract as shown. Nice, yeah?
Can I see your picture?
Which picture? This one?
No.
Oh, wait, this one?
No. Go up.
This
Yes,
one?
yes.
Ah, no, you don't want to write this, do you? It's so ugly. Okay, fine.
I will make it.
You'll make it beautiful. Okay.
Box.
What?
Teacher, he's very new this numbers.
Good. It's better than mine, yeah?
Ah.
Why don't you just copy Sophie's? I'll just continue, yeah? Okay. Right, so a little bit of vocabulary. So two waves are coherent if they have a constant phase difference. Yeah. Superposition is the idea of the, so superposition means that this height plus this height makes the new height. That's superposition. Okay. So two waves are coherent if they have a constant phase difference and the same wavelength.
What's the phase difference again?
Well, I'll explain what the phase difference is. The time difference between the peaks. So, like, if you look at this example, look.
Wait, where's Patrick?
We know Patrick's not here. He went home. Look here. So, let me see. Peak. Yeah. Let's not look at this one. So, look. Here's the peak of the first wave. And here's the peak of the second wave. And you see that distance together is the same. And then when we look at the next one, here's the peak. Can you see? And here's the peak, and the distance between them is the same. This is the phase difference. Okay? It's all the same. Oh, yes? You know this word, phase difference? We did it earlier today. Phase difference is this. It's all the same. Also, the wavelength is the same. So I don't have a ruler, but if you measure the wave, peak to peak is this much.
But the phase difference is only in the peak and...
Peak to peak. Yeah, so look, the phase difference is the same each time, and the wavelength peak to peak is almost perfect. This much. And then for the other one, peak to peak,
15.
20 centimeters. The same. Yes? So for coherent, you need two things. Constant phase difference and same wavelength. That's coherent. Those two things.
I should start bigger one.
Yes, please. It'll help me.
Wavelength.
Yeah, one peak to peak or trough to trough. Yeah.
What is trough?
Huh? What's trough? You know trough. Yes. Remember, good.
Coffee.
I needed my third cup today.
Third. Oh. How
Are
many
you
cups
addicted
is
to coffee?
No, I just needed. I needed.
how many cups?
I had a lot. I had you for 2 hours, which is a lot, and then I had business for 2 hours, and now I have you for 2 hours again.
So one for each class.
Yes, actually, yeah, it was one for each class. All right, continue.
No.
No, okay. You have this? Continue. Yeah. Okay. So next. So when two coherent waves propagate together from two different sources, eventually their peaks will meet. We say the path difference is the difference in the distance each wave travels. So I need to explain this with a picture again. So these two waves are coherent. So that means their wavelengths are the same, and the distance between their peaks the same. So these are coherent, and these are coherent. And what they're saying here is eventually their peaks will meet. So you might say, well, if the peaks are the same distance apart, why do they meet? And what's happening here is, if the waves were like this, like in the last picture, the distance between their peaks will be the same. But because they're at an angle, the peaks will start moving closer together. So if we try and go back for a moment to this picture here. So you see it's the same distance. But then if I was to turn this down at an angle, then this distance is decreasing.
But what if it's like that?
No, then they won't meet. Yeah. But if I turn them down, these distances are decreasing. But we still say constant phase difference.
Because the uniform decrease.
Well, no, just because if they were parallel, it would be the same. So anyways, here, so when two coherent waves move together, their peaks will meet. We say the path difference is the difference in the distance each wave has travelled. So for example here, their peaks meet here. How far has each wave travelled? Well, in the picture you can see they've travelled the same distance, so the difference is 0. In this picture, which wave travelled more, S1 or S2?
S1.
S1. So the difference is the distance of S1 minus the distance of S2. In this question, the path difference is half a wavelength. I won't worry about that right now, but I want you to understand that the path difference is this one minus this one. But what's important is that at the end, at P, this is where the peaks of the wave meet, at P here.
So is S1 minus S2?
Yeah. Yeah.
The peaks of the wave meet.
Yeah. Now, if the waves were going parallel like this, the peaks won't meet, and the difference between them is constant. Jess, got this?
Screen.
Huh?
Screen.
Screen. Board.
Oh.
Ah, you know screen. Continue. Yes? Amanda? Yeah. Yes. Corinne?
Fluid.
Only right on the last line.
Continue. So we have two types of interference. We have constructive and destructive. So constructive interference is when the waves combine to form a bigger wave. Have a guess at what destructive means.
Combine to form a
You're right. Smaller wave. And what about completely destructive?
becomes just zero.
Yeah, completely destructive means the wave cancel, no wave afterwards. So it means every time there's a peak for one wave, there's a matching trough for the other wave to cancel it. So we have constructive, destructive, and completely destructive. So here's destructive, the wave completely destructive actually. The waves combine and they cancel. And here's constructive. The peak with the peak makes a bigger peak. The trough with the trough makes a bigger trough. So destructive, completely destructive actually, and constructive. So you don't need to write all of this down. Just write what you need. You need to write all of this? Yeah.
Like completely destructive.
That's actually completely destructive, yeah. Yeah.
Should I draw a picture?
No, you don't need to draw it. Only if you...
The same?
Yeah, this is the picture for constructive, yeah. You're drawing the picture. Okay. Yes. Yes. Continue. Okay. Amanda?
Yeah.
Okay. Hey, look at this picture. Remember this?
No.
No.
Double slit.
Yeah, so
Young's double
Young's double slit experiment. So, as you well know,
Nice to meet you.
yes, nice to meet you indeed. You well know that when a wave passes through a double slit, the image you get on the screen is this.
fringe.
Yes, I don't even have to say it, okay? So that, you know this is called Young's double slit experiment. So if two coherent waves emitted from 2 point sources and then later superimposed on a plane, we find that the wave produced on the plane will have maximum minimum intensities. In other words, if two light waves meet, then we'd have an alternation between bright and dark on the screen. If they were two sound waves, then we would have regions of loudness and quietness. So look, there's a lot here, but I don't want you writing this down. I want to explain it with a picture, and then you can write it down. So, what's happening I'll try my best to draw this to explain why. Here's the screen, and you have two waves coming out here. So it travels outwards like this. This is called diffraction. Remember, diffraction spreads out. So diffraction. So just to be clear, every time I draw a blue line, that's a peak. I'm looking at the top. So we have peak, 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 peak like this. And here we'll draw it as well. Peak, 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 and so on. Now let me draw the trough in light green. So in between the peaks there's a trough. You know what a trough is because you told me 1 minute ago. Lowest, minimum, trough. You just.
It doesn't look like.
I know. Because the wave is it's because you're looking down on it. The wave is going like this, and I'm looking down as it spreads out. Think of like an ocean wave. Yeah. So this is like an ocean wave. It could be an ocean wave. This could be a water. Right. So there's trough, and here in dark green, trough, 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 and trough. So look what happens. Here, peak meets a peak. That's constructive interference. So right here will be a very big wave, a very big peak. Also like here, and like here. And so when this big wave hits the wall, you get a big wave here. Now look at this. This trough hits this peak. So what happens here? The trough hits the peak. Very small. So this will be small. So here is like no big wave, but here is big. So you'd have a big wave, no wave, big wave, no wave. This is why you get the picture on the screen. The peaks meet peaks to make a big wave, the troughs meet a peak, no wave. This is called two-point source interference pattern, or as we said in the quantum mechanics lesson, fringe pattern. But that's the full name. I just want you to write this name down. Two-point source interference pattern. So if it was an ocean wave, then we'd have big waves and small waves. If it was a sound wave, what do you think that would represent if these were sound waves? What do you think? Loud, quiet, loud, quiet. And if it was light, it'd be bright, dark, bright, dark.
No, I thought sound is transverse wave, but it doesn't attach to the wave.
Yeah. So a diffraction gradient is just a piece of plastic with many slits in it.
The longitudinal wave is the one like that, right?
No, the longitudinal one is like this.
Okay.
Yeah. Right, so just again, wait. I just need you to write the name down. And here's the picture of it. So this is the diffraction grade. It has many slits in it. Yeah. So when the light passes through, it spreads out.
This is the polarized.
No. Don't think. Could you use it for polarizing? I don't think you can. I think polarizing one. I don't actually know if there's much of a difference. The slits might need to be smaller for it.
Is it used to the bubble?
Yes. This is the double slit. The light comes through and then spreads out. So just write down the name, and if you want, you can try and draw the picture. This is a diffraction grating.
Similar as bubble slit.
It is the double slit because what happens is the light comes through and passes through two of the slits. So you know the light is very small. So the light comes along and hits one of these and passes through two of the slits. So the reason we have many of them is because slit, you know slit? This is a slit, S-L-I-T. Yes? You're not writing it, are you? No, I don't want you to write this. I just want the name and the picture, that's all. No, okay. Right, so some vocabulary. Slit separation, we use the letter D. This is the distance between the two sources, the two slits. So actually, if I go back to my picture here, no, it doesn't matter. The distance between the holes, between the slits, that's called the slit separation, and that's a D. The distance between the two sources. Fringe separation, what do you think that is?
The distance between the fringes.
Between the bright spots, yeah. Okay, the next thing is the angle. So this is the angle the light travels at when it leaves this diffraction grating. So the angle is theta, of course. The angle the wave makes with the normal. So, you know, the usual. Distance to screen. Well, that's the distance between the source and the screen. Big deal. And then the order, n, is the position from the center. So I'll explain this with a picture now in a moment. I'll explain with a picture. Can I draw the picture? Okay. So, actually, yeah, here's my picture here. So, I'll draw it on this picture. So this here is the small d. Now, look here, you'll have, I'll try and put it in red, you'll have bright, dark, bright, dark, bright, dark, bright, dark, and so on. Come on. Okay. So, Amanda, this is the n. Here we say n is 0. Here n is 1. Here n is minus 1. Here n is minus 2. Here n is 2. The d, the big D, is this, the distance between these spots. The distance between the bright spots is the d. That's the d there. And the angles, well, for example, what's this angle here? 0. This angle here is like theta, whatever, 30, and this angle maybe 45. So these are the angles, and this angle here would be minus 30 and minus 45. These are the angles. So we could say something like theta 1 would be the angle to this one, theta 2 maybe is the angle from here to this one. Did I leave any letter out? No. Small d, big D, theta and n. Okay. Continue. I know you. Oh, sorry, S. Oh no, sorry. Ah.
Isn't
No. I know. No, it's not D. It's not D. So sorry. It's S here. And this distance here, that's the D. Thank you, Sophie. Oh, of course, now it makes sense. Yes. You can't see it, but the theta is the angle here with the normal and the line from the center to the dot. Yeah? Oh, you're not drawing this, are you? It's so ugly, though. Yeah? Can I continue? Okay. Ah. Okay. S is between the ends.
Each is one circle.
Yeah. So this is n0, -1, -2, 1, 2. Now, please note, the S is, are we listening? You're not listening, you're texting some girl in business, aren't you? Aren't you? Be honest.
Go on.
Okay, fine. The S is the distance between the bright spots. Now, technically, the S is not the same. They're different, but they're nearly the same, okay? So often we can say that the S is about the same distance each time, but it's not quite the same. In fact, what's happening is the S is getting a little bit bigger each time, okay? Right. We have two formulas for this experiment. So here are your two formulas you need for these problems. N times lambda equals d sine theta. So this formula can give you the theta for whatever n you want. So for example, if the n is 0, what's the theta?
0.
Yeah, of course it is, because it goes straight across. And then this one can give you the fringe separation. You got those formulas? Continue. Approximate. Yeah, this formula is exactly right, but this formula is only roughly right, because remember I said the S's are not quite the same, they're getting a little bit bigger. So there's a little error, but it's acceptable. So here we have our question. Now just relax, because there's only one question, this one, okay? What? Look at all. Hey, look, you have no, you get this in a minute. You have the whole week to do it. Okay.
Every time I study, have whole week.
You can write this or draw it, whichever you prefer. This paragraph. only one question.
Ah, this is what you said 1 hour ago.
One question, just A to H.
Wonderful.
Mm. You got the information?
I choose practice English.
Practice English is good.
No, my English is pretty good.
Yes, practice English. I'm Batman. Just practice this English. Yep.
Yes.
Yeah.
Are you watching it tomorrow?
Maybe not tomorrow, I think it'll be too busy. So everybody will be going tomorrow.
Yeah. I don't want anyone tell me
Yeah, if you
what
but
happened.
the longer
I want to
the
be
longer
present
you
so
wait,
so
the longer you wait, the more
yes.
you know,
That's true. That's
the
true.
more spoilers.
Well, we all know Batman's going to win because he's Batman.
Yes.
Yeah. And Wonder Woman is in it as well.
Who?
Wonder Woman.
Oh.
But I heard she'll have a movie next year as well.
Yes, yes.
So who's on Batman's side?
Yeah, I don't know. Alfred.
I don't care because I know the best on the hit.
You don't care about what?
Who is inside? I only care about Batman.
Okay.
Because he's the first superhero I like.
Oh, good. Batman.
Yes.
Yeah.
What's your first?
I think it's either going. Oh, I don't remember. I can't remember. It's going to be either like Batman, Spider-Man, Superman, or maybe Turtles, or Transformers. Yeah. All right. Have you got this? Can I do this one?
10 seconds.
10 seconds.
No longer. The first
Humming.
what's that?
Making a sound. Buzzing. Yeah, like this. Good yogurt.
I don't know why today is cheaper than normal.
How much?
1.5.
It's okay. How much is it normally?
2.7
Expensive.
or 2.3, so I don't buy.
But today you will buy it. Okay. All right. You got this? Yeah. So let's have a look at this. What's happening? So you have the hall, and you have a person walking along the hall here, and this distance here, I think I said was 2 meters, and then there's a speaker here, and it's making some sound. So then the sound comes out here, and then the sound comes out here. These are doors here. And the distance between the doors, I think I said was 1 meter. And the frequency here, I said, is 2 kilohertz. Yes. Now, what I didn't actually say in the question, which I need to also give you, is the speed of the sound. Does anyone actually know what the speed of the sound waves are? No, 330 meters per second.
Well, we should know.
No, you shouldn't. It'll be given to you. I'm giving it to you now. Okay, so what will happen to the man as he's walking? Well, in some places he will hear very loud music, but then in some places it'll be quiet, and then it'll be loud again, then it'll be quiet, then it'll be loud again. Now actually, in D207, they have 2 speakers on the wall. So next time we're in D207, I can do this. I can play the sound, and then when you walk across the room, it goes loud, quiet, loud, quiet.
Why don't you need 2 slits?
Yeah, but I see there's 2 speakers, and you can have the sound come out of both speakers, like the 2 slits. So in the room D207, if you picture it like this, you have a speaker here and a speaker here. I can play a certain sound, and when the sounds come out both, you get parts where it's peak, and then parts where there's no sound. So then I'll make you walk across the room, and as you walk across the room towards the door, you can hear the sound go up, down, up, down, up, down.
What if it's during the listening test that someone sits in the middle there?
No, because it only works for sound which has a nice pattern, wave shape to it. Sound of people speaking, like when somebody speaks, the sound wave looks kind of like this. It works for nice smooth waves only. Anyways, first question is what is the distance between these here? So that's S, isn't it? And that equals lambda d over d. Do we know this d here? We do. What is it? Can anyone tell me? This d here, this big d, what is it? 2 meters. That's the d here. What about the small d? What's that? What is it, yeah? It's 1 meter.
Yeah.
Do we know the wavelength?
No.
No, but we have this formula, V equals F lambda. So lambda equals V over F. So that is 330 divided by F.
But
Yes?
do you know the S?
Which S?
The big S.
No, that's what we want.
Oh.
So now I know the lambda. So if I put that into my formula as well, I can get the S. Lambda times big D divided by small d, and the answer is 33 centimeters. So every 33 centimeters he hears a loud peak.
Between the door, one.
1 meter, yeah.
From where to where is 1 meter?
Good question. I was hoping you wouldn't ask that. I think it's, I think it's this distance here, but maybe it could be from the center to the center. But the point is, it doesn't matter for the question. They'll give you this number and you use it, but I think it's here to here only. I think. Okay, what was the next question? The next question is the angle for the second order. So here this is n is 0, this is n is 1. So what they want is the angle here to n is 2, this angle here, theta. So we can use the formula n lambda equals d sine theta. What's the n? 2. The lambda, 0.165. The small d is 1 and sine theta. So let's get theta. .3 degrees. Grace, come on. Are you writing this down? No, you're not.
Yes.
You got this part?
Yes.
Great. Okay, next, continue. Next part is, what is the maximum order? And I give you a little hint. The theta must be less than 90, because if you look at the picture, if the theta was equal to 90, what would happen? It wouldn't hit the wall. So the theta must be less than 90. So theta must be less than 90. That means sine theta must be less than 1. So n lambda equals d sine theta.
This is for C.
Huh?
This is for basically C.
Yeah. Theta must be less than 90. What happens when theta is equal to 90? What do we get for sine theta? Actually, yeah, it's equal to 1. So this is like the limit. You can't have more than 90. You shouldn't even have 90.
Why?
Huh?
We have more than 90 again.
Because it would mean it wouldn't hit the wall. It would just continue straight up.
Okay.
So that means n lambda equals d sine theta. But n lambda must be less than d, because the sine theta can't be 1, because that's 90. The sine theta must be less than 1. So the n lambda must be less than d, because the sine theta here must be less than 1. So that means n must be less than d over lambda, which equals, what was the d? 1, and the lambda 0.165. So what's the biggest the n can be? No, because n goes 0, 1, 2, 3, 4, 5. 6 is the maximum. Yeah? D divided by lambda is 6.06. D is 1, and lambda is here. Is the lambda.
Why is n lambda smaller than d again?
Well, it's smaller than d times 1 because sine theta must
Oh,
be less
okay.
than 1. Yeah? Yes? Last part here for this. So how long until the boy doesn't hear the sound anymore?
Very long.
Not that long. So, if you look at the wall, how many orders do we have? We have 6 orders. 0, 1, 2, 3, 4, 5, 6. But we can also go the other way. -1, -2, -3, -4, -5, -6. So how many S's is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the total distance here for the sound wave is 12 S's. Where's my pen gone? 12 S's. What did we say S was? 33 centimeters, wasn't it?
Yeah.
So the answer is about 4 meters, 3.96 meters. So, after 4 meters, he shouldn't hear anything anymore. Does anybody have 2 speakers at home?
I used to.
We can have like 2 laptops and then.
No, it needs to be 2 speakers.
But not here.
But laptops have speakers.
It work better if you can separate them a little bit.
KJ has one speaker.
He does. You can try this at home if you want, okay, after you try your microwave example. If you have 2 speakers, what you can do, put 1 speaker here and 1 speaker here, and put them about a distance of 1 meter apart, and then have them play a sound. I'll tell you what sound to play in a minute. And then what you do, you sit in front of the speakers, and then just move your head left and right. So you sit here and you move your head left and right, and this should make you hear the peaks and the troughs as you move it. Now what you would need to type into YouTube is something like sine, sound, test, wave, 2 kilohertz, or something like this. So this will make a nice, smooth sound wave of 2000 hertz. You can try it when you get home, and you should, as you move your head, you should hear the volume go up and down as you move left and right. And if it doesn't work, what you can try is try different frequencies and try different distances. But let's take this one as an example. So how far apart should the slits be? The separations. That's S. What's the formula? S equals lambda d over d. So if I'm using 2000, that's 0.165. So how far away will you be from your speakers? Let's say that's 1 meter as well, okay? So if it's 1 meter and 1 meter, that means the distance between these should be about 16 centimeters. So when you move your head 16 centimeters, you should be able to hear it increase and decrease. Now I've done this before in D207, and it does work. And who actually can try this at home? Who has speakers?
No, why did you take 2 separate laptops? Can that work?
No, because the sounds need to be in phase at the same time. No, it needs to be 2 sound sources. Not going to work.
It's moving, I can hear.
No. You can ask, KJ has 2 speakers, does he? Like, I mean 2 speakers that you can separate, a left and a right. KJ has this?
Who's KJ?
I
You know KJ.
But I know he buy his speaker at Penny.
Okay. You could go to D207 and try it with the speakers if you wanted to. Okay.
Please take us trip.
When's we're in D207 on Monday, aren't we? Normally. I think we're in D207 on Mondays. Normally. Yeah, so next time we're in D207 we can do it, okay?
Can you finish in 15 minutes?
I think we can't do the second class today. So what I'll let you do is
What is the topic in second?
the last lesson, which we'll have to do after the holiday break, is stationary waves.
What is second?
How big was this lesson? Let me see.
Easy peasy course.
Easier, yeah, easier than the last two lessons.
Easier than
The last two. But how big is it?
how many pages?
Yeah, 12 slides. How many questions?
Let's do after break.
Sound waves.
I hate this.
What is
You
same-
hate this?
What is same picture?
It's difficult one.
This is
It's
difficult?
51
Remember
pages.
this?
I need to.
No, it's not really.
Look at
I know it's not 51.
Yeah, it's difficult one.
Yeah, okay, you want to do this after the break, I think would be better.
hard to draw picture. Somebody is doing some music.
Yes, yes.